that all second order stationary points are uniformly bounded. While we are able to show this for compact SDPs, translating this from the convex setting to meaning even if the original SDP is actually compact, when we are looking at the penalty formulation in the non-convex world, it's a priori not clear that you cannot have second order stationary points somewhere far away. So that's one of the challenges that arises here. And so this basically finishes the second part, where we showed that if you have an approximate first order stationary point, its smallest singular value is very small, right? Approximately rank deficient. So there was the other step that I did not talk about previously, which is that if you have an approximately low rank second order stationary point, meaning that I have an approximate second order stationary point and it has a small smallest singular value, then it's approximately global optimum. So let me try to give an intuition of why this is true when there is no approximation involved, right? If I have a second order stationary point which is rank deficient, then it's a global optimum. And the reason for this is that the original function f that we are considering is convex, right? And if you consider a point which is suboptimal, so if u is suboptimal, it means that u transpose in the original space is also a suboptimal point, because f is convex, there is a descent direction, okay? And using singular value decomposition, you can actually get a descent direction which increases the rank by at most 1, okay? So given any suboptimal point, you can actually find a descent direction which increases the rank by only 1. And because u was rank deficient in the original space, you have all the directions which increase the rank by only 1. So there also exists this descent direction which increases the rank by only 1. Okay. So we are crucially using the convexity of f in the original space to be able to say that if u is approximately rank deficient, then we can construct a direction that does not increase the rank beyond whatever our domain allows. Yeah.
So why does the direction exist in the factored space? Because this factored space of
low dimensional, but we are saying u is rank deficient with respect to. So if we are working n cross k, u is k minus 1 rank, right? And any direction which increases the rank of u by 1 exists in the factored space. And I'm saying that if the original function was convex, I can actually find a descent direction which increases the rank by only 1. So that descent direction also exists in this low rank space because the point that I'm considering is rank deficient. It has rank only k minus 1. Okay. So let me summarize the content of the talk. So as I mentioned, like low rank solutions to semi-definite programs are useful both from algorithmic as well as application perspectives. And the Burer Monteiro approach tries to leverage this idea to directly work in the low rank space and be able to find low rank solutions. We first show that it may not work in the worst case, in the sense that there exist bad second order stationary points and we don't know how to avoid them and only converge to global optima in the factored space. But this does work in the smooth analysis sense whenever there is some amount of perturbation. So for large classes of problems, this will end up working. Okay. There are several important open directions in this work. So firstly, we believe that our results are not really tight in terms of the dependence on the dimension as well as in the accuracy parameter. And okay, so I'll get to a bit more detail about this in the next slide, about what exactly I feel is suboptimal and how one can possibly try to improve them. The second line of things that we believe are suboptimal in our results is that our results mostly apply to the penalty formulation, whereas augmented Lagrangian methods are much more popular in practical usage for solving semi-definite programs or even a large class of constraint optimization problems. And we have some preliminary results for exact augmented Lagrangian methods, but we don't have any results for inexact augmented Lagrangian methods, which will be much more useful from a practical point of view. Finally, because we did not make any other assumptions on the semi-definite programs, we were able to guarantee solutions of rank only square root m. But in most machine learning applications where you assume much more nicer structure on the problem, such as in matrix completion and so on, you would expect solutions of much lower rank than square root m, and developing algorithms which can actually directly tackle a large class of problems and use the special structure in those problems to get to much lower rank will be very interesting to do in this context. So now let me first tell you why exactly we believe our results are not tight, and I think it also leads to a very interesting random matrix theory question, which I'll point out. So the main bottleneck in our results is that we first did this high large deviation result for a random Gaussian plus a fixed matrix, and then we used epsilon net to extend it to the entire space, right? I think this is suboptimal, and I'll tell you why. So if you consider the question, what is the distance? So if I take a random Gaussian matrix, okay, so I'll give you a subspace, and then I ask you the question: if I pick a random Gaussian matrix, how far is this Gaussian matrix going to be from this from this fixed subspace? This answer is very well known, right? Because you can just think about these as vectors. So I have a subspace, and then I have a random Gaussian vector. Then the distance is going to be dependent on the dimension of the subspace, and whatever is the orthogonal dimension, the distance is going to be dependent on just that, right? Similarly, there's been a lot of work in random matrix theory on understanding if I give you a random Gaussian matrix, what is the distance from the set of all low rank matrices? This boils down to understanding what is the typical value of the smallest singular value or a particular singular value of the matrix. Okay. The question that arises in our context is so if I give you a subspace and the set of low rank matrices, and I ask what is the distance of a random Gaussian matrix from the Minkowski sum of a subspace plus the set of low rank matrices, this question is what we are unable to answer very tightly. And we do this epsilon net argument, which gives us some result, but I think there should be a much cleaner result for this question, which is about I give you a fixed subspace of say dimension k, okay, and I give you a set of low rank matrices where by low rank I mean of rank n minus k, okay. If I take a sum of both of these, so I take any matrix here, I take any matrix here, and then I take their sum. So the set is of the sum of all matrices from both these sets. Then if I take a random Gaussian matrix, what is the distance of a random Gaussian matrix from this set? So this is the precise random matrix theory question that arises here, and answering it like with the correct result will be directly applicable in this result, and I think will right away improve the results that we currently have. Okay. So that's all I wanted to say. Thank you. Yeah, and I'm saying that gives you some result, but I don't think it's tight. Yeah. Yeah, yeah, yeah. Yeah. So people have looked at top singular value and then also the smallest singular value even for like more general classes of matrices. But if you ask somewhere in the middle in the spectrum and then ask what is its typical value, not much is known for non-Gaussian random matrices. Yeah. Yeah, I think the union bound argument is low. Eventually, like we want to understand this. So maybe let me try to illustrate it more clearly. Yeah. 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 Square root n away from the tail. Yeah, almost all the way. But I think there is still significant difference. Like as Piyush was pointing out, for the last one, you cannot get exponential concentration, whereas for these ones, you can get exp of minus k square, right? So it's already exponential in n. Yeah, maybe the last point I can try to illustrate. So what I'm asking is, so I have a random matrix G, and let's say S is a subspace of dimension m, right? And let's say Lk is of matrices So I want to say that this cannot be too small. Once k is greater than or equal to square root m. SP? Okay. Even for somewhere in the middle of the spectrum? I see, okay. It's like Talagrand's concentration of measures. Okay. Okay, okay. Yeah, I mean, once you have just the spectrum, then you can use this epsilon net argument to cover part of this, and then use this argument, but it will not be tight in general. At least for Gaussian, it seems like this kind of thing should be known, uh, but I don't think it's known. I find it very interesting. All right. Is it embarrassingly early? Thanks.